Front Finder. Before I get into it, this is work that I did at OU as part of my master's work. Basically, train an AI model to predict fronts. So what I'm going to do in this presentation is I'll talk about why we decided to pursue this work, and also talk about some other improvements that I've been trying to make to this model as well. So also like to give my thanks to Amy McGovern and John Allen, who have assisted me throughout my time at University of Oklahoma. So the main motivation behind this work is that frontal boundaries, or weather fronts, they're associated with many high impact weather events. Frontal analysis, or the process of drawing fronts on a map, is still largely a manual process that is performed by professional meteorologists. So meteorologists at NOAA, they draw fronts over North America and much of the Northern Hemisphere several times per day, although I believe the Unified Service Analysis, I believe that might be going away soon. But regardless, right now they draw fronts over North America and the Northern Hemisphere. And so the goal is, can we develop an automated approach that streamlines and reduces subjectivity in the frontal analysis process? So in this figure from Occhiolini et al. 1992, this is a map of fronts drawn by participants at a meteorology workshop. So the solid lines here that you see are the fronts that are drawn by the actual forecasters or meteorologists. And you can see that near the low pressure centers, there's generally good agreement. But then as you get further away, you can see that the fronts kind of fan out in all directions. And so the goal here is to develop an automated approach that, one, reduces the subjectivity in the frontal placement and also just makes it quicker and more consistent. So some background here, I developed the Front Finder AI model, which is a machine learning model that is based on the UNet 3+ model architecture, and I'll get into that in the next slide. And it can locate cold, warm, stationary, and occluded fronts and dry lines, and it can actually discern between the different types as well. So it was trained on 12 years of ERA5 reanalysis data over CONUS using 10 variables at 5 levels, 5 partial levels that you see on the right side of your screen. So Front Finder can correctly classify about 3/4 of what we're calling the ground truth fronts drawn by NOAA. So the labels that the model was trained on were the fronts from the Weather Prediction Center and the Ocean Prediction Center as well. And it can classify about 3/4 of these fronts. So especially with cold fronts and dry lines, your probability of detection is in the 80 to 90% range at 250 kilometers, with false alarm rates below 30%. So in the summer of 2023, I did an internship at the weather company and operationalized Front Finder into their system, as well as a new system that I'll be showing as well. It's a new version of Front Finder that performs a little bit better in the Southern Hemisphere. But it's also running operationally right now at the Weather Prediction Center with generally positive feedback from meteorologists. So the UNet 3+ model architecture, I'm not going to go into the super fine details of this, but the general idea is we input a 3D image with dimensions latitude, longitude, pressure level, and then the last dimension here is the number of variables. We extract some 3-dimensional features from the input map. So basically the model is actually explicitly resolving 3D features. And then we do a process called max pooling, where we shrink the image down, cut the dimensions of the latitude and longitude in half, and then pull more features off of that. And the idea behind the max pooling and then taking more features from it is when we shrink the image size down and then apply the same filter size across the image, we can get features that cover a much larger area. So we repeat that a few times, and then we upsample the image back up to the top. And then at the end of the model, we actually do a special convolution that collapses the pressure level dimension down to 1. And then we get the probability of cold, warm, stationary, occluded fronts, and dry lines at each point. So the really neat thing about this is that you can input a 3D image, and then the output is a 2D map of the frontal predictions. So, and I do have a paper published on this, which is right down here, and I'll post a link to this after the presentation as well. So the cool thing about Front Finder is, since it was trained on ERA5 data, which is on a 1/4 degree grid, that means it can ingest data from the GFS or even the ECMWF, which does run on slightly higher resolution, to produce a forecast of global front positions out to 2 weeks into the future. So this plot that you see here is, and I will animate this in a second, but it's an example of the front finder prediction. So the contours here are the probability of a front within 50 kilometers of a point. And so the blue is cold, red is warm, green stationary, purple occluded, and then you'll see the dry line show up in the southern plains a few times. So if I loop through this, you can see that the model shows what you would expect to see with your typical cyclone structures. In the southern hemisphere, there is still some work to be done, although this is the new version that I retrained so that it works better with southern hemisphere cyclones, which of course spin clockwise rather than counterclockwise like they do in the northern hemisphere. But generally, it's doing a pretty good job at resolving fronts, and it looks like generally what you would expect to see. So you see the dry line that shows up in the southern plains there. And the neat thing about this is that it can discern between the different front types. So you don't have a label, the same label across all the fronts, and then you have to do some manual processing afterwards. The model can explicitly predict different front types just from the input data itself. And so operationally, this does run on GFS. So there are some pitfalls in some areas for improvement. First of all, Front Finder doesn't ingest satellite data, which is commonly used by the WPC and OPC meteorologists when they're doing the frontal analyses. It can also not classify baroclinic troughs, which constitute a large fraction of the boundaries drawn by WPC meteorologists. So in the surface analysis here I have on the right, you can see the warm front, stationary, cold, etc. However, these dashed orange lines are the baroclinic troughs, and you can see that they're encompassing about half of the fronts, or half of the boundaries just in this image alone. So Front Finder cannot explicitly find these, although sometimes you will see like weak cold front contours around them, but it can't explicitly predict baroclinic troughs at the moment. Also, you have complex systems of fronts that occur with numerous fronts being right next to each other. So for example, here in southeastern Colorado, you have a stationary front, a warm front, and then two troughs right next to it. So being on the course ERA 5 grid that we're on with 25 kilometers approximately, or quarter degree, that you can't really pick out the fine details of the features like you could with something higher resolution. So we have proposed the following research questions, and again, this work is right now is kind of on hold because I'm doing an internship at Raytheon, but as part of my PhD work, we're looking at, first of all, can we achieve greater model performance by introducing satellite into the workflow? Can we exceed the performance of Front Finder by training a model on higher resolution NWP data, something like the HER or the RRFS, which is coming into operations relatively soon? And then also, does the high resolution NWP data allow the models to accurately resolve fronts and troughs in close proximity to one another? So those complex systems of fronts where multiple boundaries are close together, can the high resolution NWP data allow us to train a model that can do that? So the first thing we did was we started experimenting with satellite data. We started with the merged IRV1 data set from NCEP and the Climate Prediction Center. It contains merged infrared brightness temperature from multiple satellites, an example which you can see here on the right. It's on a 4-kilometer grid, which we did downscale to match the ERA 5 resolution. So what we did was we trained 10 models that have the same architecture and the same time steps as Front Finder. So we're taking the same data set from Front Finder and the same architecture, and then we trained 10 additional models with the infrared data, and then we trained 10 models without the infrared data over the CONUS. And what we found was that there was really not any statistically significant performance gains. If anything, they were actually slightly worse. But generally speaking, the performance was indistinguishable between the models with satellite and the models that did not ingest the infrared satellite data. However, they do appear to be better at resolving wrapped occluded fronts, which you can see very well on satellite and was one of the main drivers for me in implementing satellite data into the model as well. So these two plots here on the bottom here are filled contours of occluded front predictions. One of the models without satellite here is shown on the left. This is the best performing model that didn't use the satellite data. And you can see the ground truth occluded front, which is this solid purple line here. The model can pick up a couple regions of it, but the probabilities are relatively low. However, the model with satellite, you can see that the model has slightly higher probabilities and can actually resolve more of the occluded front. So this seems to have helped with the occluded fronts, but again, generally, just from a pure performance metric standpoint, there doesn't seem to be a whole lot of difference between the two. We also did ingest GOES data into the model. So we actually took specific bands, like the water vapor bands, the brightness, temperature, and we also did a visible satellite as well. And we got basically the same results. So there was no difference between the models that did not have satellite data and then the models that had the GOES data or the infrared imagery. So now we've been playing with this idea of developing some high-resolution front finder models with the HER. So this is laid out on a 3-kilometer grid over the CONUS, which should allow us to get some better resolution. And in theory, we should be able to produce more detail with these front positions compared to a model that's trained on ERA5 reanalysis, which is on a grid that is, much more coarse. There are some trade-offs to this, though. First of all, the data set size is a bit insane. There are 50 times as many grid points on the HER compared to our training domain over CONUS with the ERA5 data. So the data set sizes are extremely large, and this makes training them really complicated because you're running out of memory constantly when training on the GPUs. And also we have to worry about things like convective feedbacks in the HER. So if you have a big convective complex that blows up and lays out you have a big MCS that lays out a huge outflow boundary, if you're running the model in inference mode and trying to predict fronts, say 48 hours out on the HER, especially in the warm season, the front positions might not be exactly what they turn out to be. And so some examples of what we've been able to do with this. So the first thing we did was we trained the model on dry lines, the front finder HER model on the dry lines, because they're pretty easy for a very small model architecture to detect. And so what we find here is on the right, you have 2 examples of a day in May of 2019. So these gold and then darker contours here are the dry line model predictions contoured at every 10% of probability. And then on the bottom here is the dry line model that was trained only on the HER data. And you can see that the corridor for the model predictions is much more narrow on the model trained on the HER data, which is what we would expect to see. And then this solid orange line that you see here is the ground truth dry line that was drawn by the Weather Prediction Center. So the goal is to make a model that can output something like we see on the dry line model, but for all front types. So rather than having these really wide corridors of front predictions, we can get more narrowed down predictions with more fine detail of where the fronts actually are. And so we did start experimenting with this with all front types. We trained the model that had the relatively good performance on the dry lines. We trained it on all of the front types. And we do see that the models that are trained on the HER output, they produce much more localized front positions, but performance is generally much worse compared to front finder. So on the left here is an example of, I believe that's the same day that I used, or one of them. You have the ground truth fronts, which are the solid lines on the plot, and then the model predictions below it. And you can see that front finder does a pretty solid job. I mean, the front positions match up pretty well, even the transition between between stationary, warm, and then stationary and cold as well, resolving the occlusions quite well. However, the model on the HER just doesn't really seem to be picking up a whole lot of detail with respect to the differing front types. It's got the positions generally well. However, especially with the warm fronts, especially with this warm front up here in the northeast, there's basically nothing there. So it does really well on dry lines, and it does decently well on cold fronts, as far as we can tell. But there's a lot of fine tuning that we need to do, and there's a lot of work to be done to get something like Front Finder working with the HER grid. So some conclusions here. So we've found that satellite data doesn't appear to really have much impact on our model's architecture to predict front locations. And this also could be because we have to rework the architecture in order to realize better performance gains. And then also, if we're looking at something like the GOES data, the operational use would likely be limited to current time, because if you're using GOES data, we don't really have a way right now to predict GOES imagery, 240 hours out or something like that. So the future satellite information, the absence of it will probably limit that to current time. And then the high resolution model data does appear to be useful in generating more localized front predictions. But again, we still have a lot of work to do in refining the model architecture, the training workflow, so that we can actually get really good model predictions for all the 5 front types and not just dry lines. And then this will also help us achieve our goal of resolving the complex systems of fronts where the fronts can be super close together, but Front Finder, the original Front Finder, isn't able to really discern between the 2 boundaries because of the coarse resolution. So some of the future work that I also plan on doing as part of my PhD, so we plan on including Barrett Clinic troughs in the workflow, maybe adding outflow boundaries as well, though I don't really think that's going to work, but it might be something to explore. We've also been exploring possibly collaborating with meteorologists to develop a model that can predict tropical waves in the Atlantic Ocean. And then also want to do a full-scale 80-year climatology of global fronts with Front Finder or some newer version of the model across the entire ARA5 reanalysis record so we can get a global long-term front climatology. And then also would like to use the model to assess the skill of front placement by the NWP models using the ML-derived frontal boundary prediction. So the idea here would be, say, taking the GFS, we could apply Front Finder to the GFS forecast to see how far out in the GFS forecast does the placement of the fronts, the skill of the front placement begin to break down. And so that's another thing that I would really think would be super cool to go for. But yeah, so that's all I got, and I'll be glad to take any questions.
Yeah, thanks, Andrew. That was great. I don't see any questions in chat. I'm just monitoring. Let me look real quick. So does anybody have any questions for Andrew? Again, I appreciate it, Andrew. And if there's no questions, we'll turn it over to Brandon. Okay, hearing nothing. Thanks, Andrew. That was great. Appreciate it.
Thank you.
Hey, Kevin, can you hear me?
Yeah, I got you loud and clear, and I can see your slides. Then, yep, I got it full screen. Yep, looks good. Thanks, Brandon.
All right, good morning, at least morning here in Norman. My name is Brandon McClung. I'm a major in the Air Force, funded through the Air Force Institute, Civilian Institute, working with Dr. Amy McGovern here, like Andrew was. I'll show some work on Boltcast, which is AI model for medium range lightning prediction. So just the general research motivation as a meteorologist in the Air Force and the Space Force are both interested in generating larger access to space for space launches, particularly down in Kennedy Space Center. Their launch count is rapidly increasing to probably over 100 this year, and they're launching 2 rockets near in the same launch window now down there, if you follow their Instagram feed. Other things that lightning impacts is both wildfire from cloud to ground lightning strikes, and then the energy sector, particularly with wind power is starting to be impacted from lightning as well. But there's kind of a gap in the literature and the operations kind of in this medium range 2 to 4 day prediction window from the AI tools. So a lot of them are primarily focused right now on nowcasting in the storm scale. So the goal here is to develop kind of a stable machine learning model, physics-based for kind of like a planning weather type scenario. So if you look through the literature is pretty full with these numerical physics-based flash rate parameterization schemes. This last year, Ken Cummins out of Arizona kind of summarized over 20 different ones with all the different literature, and they found several common denominators focusing primarily on reflectivity, temperature, vertical velocity, and hydrometeor mixing ratio, that go into those parameterization schemes. So I use that kind of as the justification for the inputs into the AI prediction tool, and then kind of then ask the next question, which model data and lightning data are somewhat machine learning ready to get something ginned up fairly quickly. So from that, I chose the GFS here hosted on NCAR's RDA server at the quarter degree. Chose that because it runs out to 4 days at a 3-hour temporal resolution. And then the GOES 16 through 18 GLM is easy to get from AWS, and then use that as the predictand, merging the satellites along the 100 degree west meridian and then counting the number of radiance weighted flashes there in each GFS grid cell, and then applying a binary mask. So the training and verification data all run from July 1st, 2019 through June 30th, 2024. And it does include all the data across all 4 model initializations. And then these are split into training, validation, and test sets based on the year. And so I have an example shown in the table there. So we get about 4,400 images for a training set and about 1,500 for validation and test. And so each of these samples is comprised of maximums of the 9 input variables across the 4-day prediction window for latitudes and longitudes that span CONUS for about 128 by 256 pixels. So just to visually show what the data look like that go into the model, we have a 5-dimensional tensor that goes into both a unit and a convolutional LSTM based model. They'll show the architectures next. But so we take the maximum in the column and then across the 24-hour prediction window, and then get the 5-dimensional tensor with the samples, the 4-day prediction, the lat long, and then the input variables. So you see the visualizations here, and then we do predict a 4-dimensional tensor of the binary outputs generated from the GLM datasets. These are all trained on one NVIDIA A100 GPU. So the unit model architecture is fairly similar to what Andrew just showed, where we take our input data and then we do 3D convolutions for the unit to allow learning to occur across the temporal dimension, which is the 4 in the block here. And then we go down, ensuring that we get down to 1 dimension in time, and then rebuild back out into the binary classification. The training and hyperparameters are shown here. I won't go into those. Those are all set by me after training several hundreds of models. The only thing I want to note is that the unit model has about 10 million training parameters. But then if I go to the convolutional LSTM model, you'll see that the total training number of parameters drops about 60,000. So I wanted to look at this particular type of architecture to see how it compares to some of the literature that are out there, because the literature, they don't always use it. Well, they have varying different ways of using this type of architecture, the LSTM in particular. And so I wanted to see if I could just get one convolutional layer to generate some scope. So just kind of show what the model output looks like over about a year. It'll play in the background. We have the labels up here in the upper right, and then kind of a preliminary GFS predicted reflectivity mass greater than 30 dBz on the bottom row for all the prediction days 4 through 1. And we see generally that when there's lightning occurring in the labels in the upper right, we do generally get lightning predicted in both the unit and the LSTM model. If you compare that to the GFS mask in the bottom row, the lightning models do perform better visually anyway, and that both the unit and the LSTM model are in fairly good agreement. So comparing a high parameter to a low parameter model, they're still pretty skillful. And that the variability from a 0, 6, 12, and 18Z model initialization are handled pretty well. So then to evaluate the model, just a classic performance diagram for all seasons here shown. So we see area under the curve of about 0.59 for the unit for day 1, and then 0.54 for the LSTM model on day 1 as well. And then we do see the decrease down to about 0.51 through day 4, and for the unit, and 0.44 for the LSTM. When I compare this to some of the things in the literature like LightNet Plus, which is mostly a convolutional LSTM model, they kind of show a 0.21 breadth score out to 6 hours. So out to day 4, I'm beating that. And then if I compare it to the HREF Thunder Guidance down at SPC, they have about a 0.44 average CSI through day 1. So I'm in the ballpark there as well. So I feel pretty confident in the model results. We all know that lightning primarily occurs more in the summer. So if I break it out in by seasons, I do see a little bit better performance for summer, with area under the curve for 0.63 decreasing to 0.54, and slightly less in the LSTM model there for all seasons. But then as I look across all of the different rotations and folds that I trained on, I do see a lot more variability in the model in the winter than I do in the summer. And then also the decreased performance in the winter with AUCs of about 0.4. But again, we do see the low trainable parameter LSTM model has similar performance in the unit. And then to kind of tease out what the model is actually learning, some XAI techniques did a permutation importance of 1,000 permutations of each variable across the sample space dimension. And we see the greatest change in area under the curve, that's on the x-axis here, occurs for CAPE, reflectivity, and precipitation rate. And then the others kind of fall sorted there by the median value. But one interesting thing to note here is that Graupel is known in lightning to help carry charge in a storm and generate the electrification that's needed to produce lightning. And here the model is saying that it is one of the least important parameters based on this permutation study. And then to kind of further understand how the model does, I generated partial dependence plots, which show the range of model inputs for CAPE, reflectivity, and precipitation rate that was seen. And then I varied the model inputs based on the kernel size of the model, and varying from 1 to 3 kernels, and then fixing those values to see how the model predictions change. So for the top row is for when the model was a hit and predicted very high probabilities over Wright-Patterson Air Force Base. And then the bottom row is for when it missed in the winter over Vance Air Force Base here in Oklahoma. And you can see for the summer case that varying the CAPE parameters didn't generate too much variability in the output, same for reflectivity and the mixing ratio. But you do notice this distinct discrepancy in the LSTM models and the dotted versus the solid line for the unit. There's about a 10 to 15% prediction bias that was generated, and that continues down in the winter case for Vance. But you do see a significant variability in the lightning prediction for the CAPE for when you start to vary the kernel size there. So this tells me that the model is highly dependent upon the CAPE inputs, and if there's low CAPE, you're going to get very little lightning probability. And then, so just kind of a general overall discussion and conclusion. I do feel like we're starting to bridge the gap in the medium range lightning prediction with the GFS and the GOES GLM. We do see in the summer that both models perform slightly better, and then that the unit is overall generally preferred, but the low parameter LSTM model still maintains skill when compared to that. And that CAPE had the largest sensitivity, while Graupel mixing ratio never really made it into the top 5. And now we do have this kind of 10 to 15% prediction probability bias between the two models, with the unit generating the higher probabilities. I presented this work at AMS in New Orleans, and then I got some follow-ups for transitioning this into the Air Force's weather machine learning platform. And then there's some folks here in the National Weather Center curious for the hazardous weather testbed. And then this work has been also submitted to AI for environmental science and is currently under peer review. And just kind of a preview of what's to come regarding AI and lightning. For me, right now working on Launchcast, which is solely for Cape Canaveral, trying to get 30 electric field mill data sites into combined with the HER data to predict lightning for them. But I'm having some struggles right now with both the loss function and trying to get that maximized. And then you could say maybe chapter 3 for me would be looking at the kind of a Horus cast model. Here at OU, we known for our phased array program, so we're going to try to do some predictability of KDP to sense the electrification aloft. And so I have some sample data from Horus playing down there in the bottom right, kind of a really high temporal resolution for a severe convective weather that recently captured a tornado over in Newcastle. So I think that about wraps it up. I have, if you're interested in the work, you can reach me on LinkedIn, or there's also a GitHub repository with the code. So I'll stop there.
Yeah, thanks a lot for that, Brandon. I just see one question I just put in chat as well. And it was basically, are you interested in distinguishing between intra-cloud and cloud-to-ground flashes and calculating the probability of the two within these AI models?
Yeah, so the idea for Launchcast is to try to do that because the mesoscale Eastern Range Lightning Information Network does discriminate between that. So I am trying to do both a regression and a binary classification for those different types of lightning.
Perfect.
Marston.
Yeah, nice talk. I'm curious though, when you verify this, are you going from clear skies or zero cloud to the first flash? Are you looking at duration and intensity? I may have missed that. What's the parameters for verifying how good this is? I mean, obviously you have to have from zero, when you talk about tape, you have to have from nothing to first flash. Do you understand my question?
So you're asking whether or not the first flash is input into the model?
No, I'm asking how you're verifying how good the model is. Is it predicting the first flash, the intensities, the duration? I know we were talking about cloud to ground and cloud to cloud and stuff, but
oh yeah, so
right.
this model isn't really tuned on that. So it's, if there was one GLM lightning flash, then the model is trained to predict that or greater. So there's no regression here. There's
Right.
only classification. So
Oh.
and there's no storm tracking here either.
Mhm.
So this is a general pixel evaluation. So it could
So
be
basically, if you get a flash, one flash in there, then you consider that success.
correct.
Okay, I see, sorry, just one more in chat there, Brandon. Are you interested in using other GLM variables like flash size or optical energy in your work?
I haven't considered that yet, but we could try. So I'll make note of that.
Perfect. Yeah, pending any other questions, Andrew and Brandon and Amy, thank you all very much from OU for your talk. Those were both great, and then we'll just keep moving on. So thank you very much.